Good morning to everybody. So in the last lecture, we have discussed mainly about the linear block code. And in a linear block code, we have gone through the encoding process of a linear block code. So in encoding process, there is a data word. Data word is to be converted into the code word. In the code word, basically consists the two part. The first few k bits are similar to the data word, and the remaining m bits are as per the check bits. So this m bits can be produced by the linear combinations of data bits. So that part we have already learned, and now here we have produced a code vector C from the data vector D by multiplying with a generator matrix G. So in generator matrix basically consists the two parts. The first k column and k row are the identity matrix, and the remaining portion is known as a parity matrix. So parity matrix is a matrix in which there are coefficients of Hij are there, and Hij belongs to 0 and 1. User is free to choose the generator matrix of their own choice, but at the same time he or she should have to take care the same generator matrix is to be shared between transmitter and receiver. So code vector C is basically the multiplication of data vector D and generator matrix G. So generator matrix consists of two part. The first part is identity matrix and second part is the parity matrix that we have learned so far. And as per this one, if the G is defined in a two parts of identity matrix and parity matrix, and if D is multiplied with this, so D is multiplied first with IK, which produce the same matrix D, then D is multiplied with the parity matrix P, that is known as a D into P, and it is defined by CP. So C consists of two parts. The first part is the data matrix part, and the second part is the CP part. CP part is basically obtained by the multiplying data matrix D with the parity matrix P. So here the system designer is free to select the matrix C as per the requirement, but it must be shared between transmitter and receiver. That should you take a note of this line, because this is very important part. Without the sharing the information of G matrix at the receiver is not able to recover the original data back. So we have taken one example for better understanding of these things. So in these examples, there is a 6,3 code. So first bit defines the number of the length of a code word, so that is n, and the second bit defines the data vector length, so it is defined by key. And there are two data vectors, 0, 0, 1 and 1, 1, 1 are there. It is multiplied with the matrix G, which is formed over here. And then finally we have produced a code vector C. So code vector C can be produced 0, 0, 1, 1, 1, 0, which is corresponding to the data vector D. So after multiplying D with a matrix C, G is provided. Then for a second data vector 1, 1, 1, we have even produced a code vector C, and that is 1, 1, 1, 0, 0, 0. So you can notice here the first k bit, means 3 bits of a code word are identical to the data vector. Then as per if you proceed as per this one, if you proceed further, so for every data vector D, we can produce a code vector C. So there are 8 combinations are there. For 8 data vector, we can have a code vector C. Now then we have discussed about the error correcting capacity. Error correcting capacity is basically defined in terms of how much error this code is able to detect or correct. So that can be defined by D minimum, which D minimum is defined the Hamming distance between the two code equal to 2t plus 1. T defines the error correcting capability in terms of number of bits. So T number of bits the error this error correcting code is able to correct. So in this case there are 3. Then if you put 3, we are getting the value of T is equal to 1. So 1 bit error correction can be possible by using this kind of a linear block code 6,3. If you want to get the better error correcting capability, then we have to increase the check bits m. M should be increased. So for a better error correcting capacity, but if m can be increased, then the code efficiency can be highly affected. Code efficiency defines the number of a useful bits in your block. So there are k and divided by the total number of bits, so it can be a code word length. So here, as per this earlier examples, the key have been obtained is a 3 and the total number of bits are 6, so 50% code efficiency can be achieved, and redundancy is 1 minus eta, 1 minus the code efficiency, that is also 50%. So here we can we have a trade-off. If you want to get the better error correcting capability, so the number of check bits should be increased, and if you increase the number of check bits which are appended at the head of a data vector, so obviously the code word length would be increased, and simultaneously the code efficiency goes down and redundancy increase. So it is a bad factor. We have to always work with this trade-off. And we even discuss about the linear block encoder. So linear block encoder is a encoder in which the input is a data vector and output is a code vector. So code vector can be obtained by this linear block encoder. We have gone through this. Now today we discuss about the decoding process. So decoding process is basically process in which the code word vector C is basically transmitted from transmitter, and the data is received at the receiver in form of a receive vector R. But R is not exactly identical to the code word C because of a noise. The noise is introduced in the channel, and because of that, whatever the receive vector is obtained at the receiver end is highly or maybe minor affected by the channel error. So some of the bits are received incorrectly. Now it is the part of a receiver to identify those bits and then correct it. So we have gone through the one diagram earlier in the earlier lecture where we have seen whatever the data are there, they are passed through the encoder that we have learned so far, and that will be converted to the code word. Code word is basically transmitted between transmitter to receiver. Now here the channel will play its role. They will add the noise in your bit, so few bits are going to change. So whatever the receiver data has been received, the receiver are not exactly identical to C. They are affected by some error and few bits are going to change, and that's why this is a duty of a channel decoder to identify those error bits, the bits which are in error, and then recover the original code word or data word back. So that this part is known as a channel decoder, and the input of channel decoder is always a receive vector R, which is affected by the noise, and the output of channel decoder is a code word C. And then the first k bits are separated from code word C and they are equivalent to data vector D. So we in this lecture we are going to learn in a detailed process about the channel decoder. So we start from here. So in channel decoding process, first we have to understand some very basic concept, and the first concept that we have to learn is how the receiver is able to identify the error, because the error is totally random. Maybe possible the first may be count in error, maybe possible the middle bit, or maybe the last bit count in the error, or maybe possible the multiple bits count in the error. So in this case there are n number of possibility are there. So how receiver is overcome this complexity to identify the error, and basically how accurately the receiver is able to identify the location of error and correct it. So we'll see this. So first we start here with the very basic concepts we are trying to learn here. The C can be defined as a D into G, where G can be composite in a two-part. IK is the known as identity matrix. This is the first part, and the next part is the parity matrix. So if D is multiplied here and here, then the first term you are getting is D into IK, so they are getting a D. The second is D into PDP. DP is equivalent to the another variable known as a CP, and D is written as it is. So this part I recall from a lecture number 1. In lecture number 1 we have derived this one. Now in a XORing operation, if you understand the XORing operation, so you can tell if there is a X input and if there is a Y, this is the XOR gate. So if we if in XORing operation here, if in the second input, this is external input, if we have the same value X, then y is always a 0. But if the here in this input is different than x, it's inverter of this, right? So that is y is always 1. So it means if you have a 0 0, then y would be a 0. If the same way you have a 1 1 here, sorry, not this one, you are getting a let's say I may write here that would be of z, and if I make the z is equal to x, so maybe a 1 1, that you are getting 0, maybe a 0 0, both are similar, then you are getting 0. So if you feed up the XORing input at the same input in both same digit or same bit in both the inputs, then you are getting the 0 outcome. But if you are making such change here, rather than x you are getting x dash, so if there would be a 1, there would be a 0, or then you are getting here output would be 1. So output 1 would be obtained if the two inputs are different, or if it simply means you can say if the 1 is basically if you are applying 0 here, so 1 would be transmitted, so your output y is equal to your input when the external bit z would be a 0. And if you are providing here 1, and if there would be a 1, so you are getting here the 0. So it means if you are providing the external input as a 1, then y would always be the inversion of x dash. Inversion of x dash. So this is a basic fundamental concept that you already learned in a digital electronics. I am not going to go, I am not interested to go in detail about this. You take a look of this. So it means if one input I make as it is, and the second input I will consider as a controllable input. So if this controllable input z I put as a 0, so your output is equivalent to input. So this XOR gate work like as a buffer, simple buffer. Whatever you feed at the input, the same you can get at the output. But if I make my external input or controllable input would be a 1, then your output is always an inversion of your input x dash. So this part you have to learn so far. So now, so whatever interesting part over here, so if I XORing the CP with the CP, then it would be a 0. It means the code will XORing with itself, that would produce a 0. But CP is basically DP. So DP XORing with CP, that would produce a 0. I replace the CP with DP in the first part, second part it remains as it is. So DP XORing CP, how we can write here? So in a matrix form, we can write here the D in the first column and CP in second, and in here it's a P, and IM means the identity matrix of size M. Identity matrix of size M cross M. M is the number of check bits, as earlier, as we have already mentioned earlier. So now what happens, if you multiply this, you are getting the same result. If you are doing this operation, you are getting the same result, because D is multiplied with P, so you are getting this first term, and then you multiply CP with IM, so you are getting identity matrix CP. So this is a simple, the matrix expansion of this equation, DP XORing CP. This is the equation, and this is simply the matrix expansion, right? You can say this is nothing else but the matrix expansion of this. And in this matrix expansion, you can note down here in earlier matrix G, we have the first part is our identity matrix IK, and the next part is P. Now what happens in this matrix, the P part is now the first part, and the IM, the identity matrix, would be a second part. So this matrix is simple known as a H transpose of H matrix. So now this matrix D and CP matrix is simple known as a code vector. We have already mentioned earlier, the first part is the we have already done here, the code vector C. It can be consist of two parts. The first part is data part and the second part is CP. So as per this one, here also we have the first part is data and the second part is CP. So this whole is simply known as a code vector C, and this matrix is simple known as a HT matrix. This matrix is simply known as a HT matrix. So now here what we can obtain here is this would be a 0. Why? Because CP XORing with CP would be a 0. So right side we have not changed. So right side remains as it is. The left side we have modified somehow. So after this modification, that we have got this part is the C and the next part is HT. So C into HT, that is known as a transpose. T for a transpose and H is H matrix, so it is known as a transpose of H matrix would be a 0. And how we can define here separately a transpose of HT, that is the parity matrix P and IM. And this HT matrix is very important because it is stored or maintained at the receiver. In the memory of receiver, this matrix is stored. And how this matrix is produced? So basically this matrix is produced from a G matrix. So if the transmitter will share this information of G matrix to the receiver, then the receiver can take the G matrix as an input or store it in memory, and after doing some process it will be produced HT matrix. This HT matrix is very useful matrix for a decoding process. Now how you produce this? So this, if you see the construction of HT matrix, so first part is the parity matrix. So in the G matrix we have to first separate the parity matrix P. This parity matrix, the first row is 101, and here the parity matrix will be put first. So this part is the parity matrix, the first part is the parity matrix, where we put here 101 is similar, this 011 is similar, and 110 is similar. So P matrix is put as it is in the first part. Now in the next part is the IM matrix, which is identity matrix. So how many check bits are there? So number of check bits M is equal to n minus k. This code is 6,3. So total number of bits are 6, and number of information bits are 3. So 6 minus 3, M we are getting as a 3. So now we form this matrix as a 3 cross 3 matrix, this matrix. So identity matrix, we have in identity matrix, the diagonal components are 1 and all other components are 0. So what how we can produce a HT matrix from G matrix is that HT matrix we can simply put the P matrix of G matrix, the P matrix as it is, and the bottom, at the bottom, that we form identity matrix of size M cross M. So that is a HT matrix. So receiver will construct the HT matrix from G matrix. But what is the basic or primary requirement is this: the transmitter have to share the G matrix to receiver. Then and then HT matrix can be constructed. Otherwise receiver is not able to get the HT matrix. So this is written here: the G matrix is shared between transmitter and receiver at the time of system design, and HT matrix is basically constructed at the receiver from G matrix. Very primary matrix to get the to start with the decoding process. Okay, so this part you have to learn. HT matrix is basically constructed from G matrix, where in HT matrix the first part is the parity matrix. It is similar to the G matrix parity matrix which has been shown in a G matrix, and the bottom part is formed out as a identity matrix with a size of M cross M. And this HT matrix is to be stored in the memory of a receiver, which is used to decode the signal. Now how basically the things work out in the next process. So formation of receiver vector. So here you can say there is a transmitter. A transmitter is sending the information in form of a code vector C1, C2 up to Cn. Then it is XORing with the channel noise. Channel noise is basically error, so it is XORing with a channel error, and then you are getting the receive vector R. So R is simply known as the code vector C XORing with E. So which bit is going to change? So that depends on this factor. If my error vector E is defined as E1, E2, E3 up to E6. So there are 6 elements are there because code vector has 6 elements. So we assume here there are 6 elements. If the particular bit of error vector would be a 1 and all other bits are 0, so those bits which are 0, they are not producing error. But the first bit of error vector is 1, it means it changed the first bit of code vector. So it is 1, it means there is an error. There is error. So first bit, it creates an error in the first bit of code vector. So at whatever the places of error vector, there would be a 1. So they produce an error in a code vector. But at those places where the error vector would be 0, so it works silently on code vector and do not produce a error. So if some things, if the error vector is known, then we can have a more this process can be more simplified, because that we can know the exact place where the error is occur. So if error vector is randomly created as 0 1 0 1 0 0, it means there would be a first bit of your code vector have no error because it is 0. There would be a second bit would be 1, so there would be error. There would be a third bit, there would be error vector would be a 0, so it will not produce error. But in fourth bit there would be 1, so that will produce error. In fifth bit there would be a 0, and sixth bit again 0. So there are two places where error vector can create error, is the second bit and fourth bit. So that is 1 2 3 4 5 and 6. So two places, second and fourth places, the error vector is 1, so it will produce error. So if this signal code vector C would be passed through the channel and reach to the receiver, so there may be a possibility that the second this second bit of code vector is infected by the error, and fourth bit is also infected by the error. So earlier if it was a 0, now because of this error it would be converted to 1, and if earlier it was a, or originally it would be a 1, because of this error it would be converted to 0, like this. So that we have to understand here. So very important part here, the error vector, the number of bits we have to the bits we have to identify which has the amplitude magnitude 1, which create error. Okay, so it is assumed if any an error bit is 1, it change or create the error in the same code bit. And if error bit is 0, it doesn't create, it works silently on the code vector and it doesn't create any error. So the receive vector R is basically the code vector which is modified by the error vector E. So it can be obtained with the combination of C and E, and that is XORing operation. This is XORing operation between code vector C and error vector E. And receive vector has how many, code vector has how many number of bits? So there are n number of bits of code vector. We are assuming maximum error is possible up to n bits. So error vector has E1 to n number of bits are there. So they have also n bits. And the receiver is obtained by the combination of C and E. So receiver has also n number of bits. So how you obtain here? So we can obtain here the first bit of R1 is basically XORing operation of a first bit. This is a first bit of code vector, bit of C, and this is what? This is a first bit of error. So the first bit, this is a first bit of R. So you can say the first bit of R can be obtained with the XORing operation of a first bit of code vector C and the first bit of error vector E. Now the second bit of R2 can be obtained with the second bit of code vector C2 and the second bit of error E2. And the nth bit of receive vector R can be obtained with XORing operation between the nth bit of code vector C and nth bit of error vector E. So that are this way all the bits are individually obtained at the receiver. So in terms of a vector, we can write R is equal to C XORing with E, where R is a vector of n bits, C is again a vector of n bits, and E is also a vector of n bits. Now, what is important at the receiver side is, here we are interested to get the code vector back, and which quantities are available at the receiver. So R is known because the receiver is collecting this information of R, so R is known. The C is unknown because whatever the data you are getting here, that is affected by error, so that is C is unknown and E is unknown. If we are sure our error has 0 0 0 0 means no error, right? So you are getting, in this case, you are lucky enough to get R is equal to C, that you are sure R is always a C. But this is not a case. They may have a random error. Receiver is not known earlier at which bit is affected by the error. So these two quantities at the receiver are unknown. One is the code vector is unknown and error vector is unknown. And by producing with some combination of error vector and code vector, the receiver is obtained, and this receiver is known because receiver is getting this information. So receiver is getting all the bits of receive vector R, and that is known. Now the case is, now we have to think in a reverse order. The R is available at the receiver, and from R we have to detect the C. So how you can get this? So if you assume that E, somehow you make some mechanism so that the information of E is available, or the vector of E is known at the receiver after passing through some processing or by applying some mechanism. If E is known, then the work becomes very simple, because then both side you XORing with the E. So R is XORing with E this side, and that side also C XORing E. That was the original obtained is similar to this. It is XORing with E. So both side of equation 1 are XORing with E. But the assumption here, this is assumption. We don't have actually E now at this stage, but we assume if E is known, then if we are doing the XORing operation at both the side, then E and E would be a 0. So you are getting C back at the right side, and left side R XORing E, you are getting C. So now you can identify the C. But what is the requirement here is E should be known. So the main conclusion of this whole story is that if at the receiver side, if we do some process on receive vector R to obtain E first, we have to do some process to obtain E first, and once the E is known, then XORing R with E will directly give us the value of C. And then how you get the data vector D back from C? So it is simple. Once the C can be obtained, so your 80% journey has been completed, because the first k bits are data bits, and hence the data vector D can be can be extracted from vector C by separate out those k number of bits. So this part we can do. So first very interesting part over here is, if you want to get the code vector C back from receive vector R, then the first that we need to identify the error vector E. Once the error vector E can be identified fully, then receive vector the operation between operation of XORing is performed between receive vector R and error vector E, and that will directly give us the code C. So there is basically looks a two-step procedure. The first step we identify E, and then in the second step we XORing receive vector R with those E vector E. Okay, so now how we can do this process? So now we will see the procedure to identify the error vector E first. So HT is known. We have already mentioned earlier, the matrix G is shared between transmitter and receiver, and the receiver is able to construct the matrix HT from matrix G. Now if Ri vector is receive vector, then S, this S is given known as a syndrome. So we multiply Ri, which is receive vector, with the HT matrix. Assume any receive vector can be available at the receiver, so we simply give Ri, means ith receive vector is available, then we multiply with the simply HT matrix. We assume this is the received and this is available at receiver, or it may be stored in some form at the receiver. So we simply multiply this, and after multiplying this we are getting the whatever we are getting, that we assign as a syndrome S. So syndrome S is simple Ri, the receive vector, XO multiply with the HT matrix. Now we have already mentioned earlier, the Ri is simply defined as the C XORing with E. So here if I put the same equation here, so it's a Ci XORing with Ei multiply with HT. If I individually multiply HT with all, so Ci into HT XORing with Ei HT. So we have already mentioned that if C and HT are multiplied there, then we are getting a 0. So as per this, this portion becomes a 0 XORing with EIST, and if something you are XORing with 0, you are getting the same thing. So you are getting here the syndrome S can be obtained as EIST. Right? So now